Dear friends of IAEE and dear participants in the 17th World Conference on Earthquake Engineering, I wish to express my sincere welcome to the new IAEE initiative named Meet the Masters. This initiative is in line with IAEE's effort to promote diversity in the research and practice of earthquake engineering and earthquake disaster mitigation. Here we try to connect legendary figures who have made outstanding contributions to the advancement of earthquake engineering with those who belong to the younger generations and will lead our disciplines now in the future. Meet the Masters are the video lectures featured with legendary figures in which we can listen most vividly to how they worked in various places and interact with other people to lead their research and practice. This video lecture features Professor James O. Gilsa of the University of Texas at Austin in the United States of America. First, a close colleague of Professor Jirsa, Professor Sergio Alcocer, will introduce Professor Jirsa and give us a brief history of his major accomplishments. The introduction will be followed by Professor Jirsa's unique video lecture, which he kindly prepared for this special occasion.
Good morning in Tokyo. Thank you very much, Dr. Nakashima, for your opening remarks, and especially for leading this great idea of honoring our Masters in Earthquake Engineering within the International Association for Earthquake Engineering. A great engineer is a person of eminent scientific and technological knowledge, as well as with seasoned professional judgment, whose value is in proportion to her or his ability for solving societal problems in practice. Professor James O. Jirsa fulfills, like very few others, this set of characteristics and performance. It is for me a distinct honor to introduce my very dear mentor and friend, Dr. James O. Jirsa, Professor Emeritus of the University of Texas at Austin. Dr. Jirsa was born in Nebraska, in the Midwest of the United States, in a family from Czech origins. He was raised in a farm and lived surrounded by European lifestyle and culture that have accompanied him throughout his life. After graduating as a civil engineer from his state university, he was accepted to graduate school at the University of Illinois in Urbana-Champaign, where he excelled in all fronts. At Urbana, under the mentorship of Professors Sees and Sousan, Jirsa contributed to the understanding of reinforced concrete slab behavior and design. In my opinion, more important than the slabs themselves were the lessons learned from his mentors. From Professor Chet Sees, Dr. Jirsa learned the meaning of always caring about the quality of a paper and a presentation. From Professor Mette Sousan, he absorbed the rigor, yet the importance of ingenuity and engineering judgment for a research program to be successful. Jim learned from both the importance of observation to understand structural behavior. Dr. Jirsa very soon developed his own style as a researcher, studying interesting and challenging topics, which were also critical for improving the engineering, design, and construction practice. In his papers, for example, besides the meticulous and thorough explanations and analysis of data, Dr. Jirsa very often concludes with a code change proposal, ready to be included in a design code or a guideline. Later in his life, he became a true advocate of the importance of structural detailing as a necessary condition for adequate seismic performance. After a few years at Rice University, Dr. Jirsa was invited to join the faculty at Texas, where he benefited from another mentor, Professor Phil Ferguson. At UT, Jim developed a stellar career as an educator, researcher, and later in his life as a university administrator. Dr. Jirsa now enjoys retirement along with his wife, Marian, visiting their twin sons, Stephen and David, and their grandchildren in California as many times as possible. Jim is a classical music fan, especially of Dvorak, book reader, and traveler. There is no doubt that Dr. Jirsa has been one of the most prominent leaders in our earthquake engineering community. He has been at the forefront of structural and earthquake engineering by making outstanding contributions to concrete research and design. His contributions include his work in slabs, joints, shear, and bond and development length. Wherever you have a properly designed beam column joint subjected to earthquakes, or reinforcing bars well anchored, or adequately spliced for development within a concrete element, Jirsa's research and teaching are present. Attending class with Jirsa was a luxury we had. For example, on the seismic rehabilitation of reinforced concrete elements and systems, we learned in class about how to connect new concrete to existing concrete, ways to improve transfer of forces between concrete and steel elements, means for increasing the capacity of the efficient splice detailing, the behavior and design of bracing systems, criteria for adding infill walls, behavior and design of frame elements jacketed with concrete shells, steel plates, or carbon fiber, or the dynamic response of buildings rehabilitated using distinct strategies. All these techniques had been studied by Jim and his students and had been transferred to practice via codes and detailing requirements. Jim has been certainly the pioneer in the field of seismic repair and strengthening. In all his research, the primary objective of his design approach has been to obtain safe, serviceable, and economical structures. Dr. Jirsa has received all awards and recognitions an academic may receive at home and abroad because of the quality and merits of his research contributions. He has served in numerous organizations and committees with the sole interest of increasing building safety and improving our built environment. Jim is also an exemplary person. His warmth and personal commitment to his students and colleagues is highly regarded. Jim is a true role model in the fullest sense of the concept. Many of us, his proud students, have so many stories that attest his integrity, professional honesty, leadership, and caring about the other person. How many times we, his students, screwed up casting concrete in a specimen, forcing the specimen to be wasted or to be repaired? How many times we applied an extra loading cycle, or even worse, we lost control of the loading sequence during an experiment? How many times we thought about being kicked out of the program because of our errors? In all these, we always found Dr. Jirsa's smile and support. Educated in a rigorous use of the English language, both spoken and written, turning in our thesis or papers for his review was scary. If you did okay, Jim would give them back to you all marked up in red. In my case, for the first chapter of my PhD dissertation, I thought I had written a piece that would have made James Joyce, the acclaimed Irish writer, so proud. Well, when Jim gave me back my manuscript and seeing his red marks all over, I do not know how my face looked like, but right away he asked me to see him on Saturday. Indeed, we went over his comments and suggestions one by one. I still remember him saying, "We have you here because you are a good engineer, not because you are Shakespeare." Well, that was very comforting. I am sure all the students of Jim passed through his rigor and learned the importance of writing with a meaning in mind. Indeed, Jim is a master, a true mentor. We know that even though we don't communicate as often as we would like, Jim is always there to listen, to provide words of encouragement, and when asked, to advise on a personal or professional issue. No better mentor could be found. A Japanese proverb says, "Better than 1,000 days of diligent study is one day with a great teacher." Please allow me to change it a bit. Better than 1,000 days of diligent study is one Meet the Master's lecture with a great teacher, Dr. James Jirsa. The floor is yours, Dr. Jirsa. Thank you very much.
Thank you, Sergio, for your generous and kind introduction. Your comments reminded me of what I like most about teaching, the great privilege of working with bright young engineers like you, and then the pleasure of seeing their careers blossom. Muchas gracias, Sergio. I would also like to express my thanks to Dr. Nakashima, Dr. Kurata, the International Association for Earthquake Engineering, and the 17th World Conference Organizing Committee for inviting me to participate in the new Meet the Masters program. I sincerely appreciate this opportunity to spend a few minutes with you to discuss my career in earthquake engineering and the things that influenced and propelled my research and teaching activities. The program was intended to encourage young researchers, practitioners, and students, particularly from developing countries and regions, to participate in the 17th World Conference. So I am so sorry that because of the pandemic, we cannot meet in person, but I will try to convey some thoughts about our role in advancing the state of the art in earthquake engineering. Unfortunately, you will miss one of the great benefits of a world conference. You will not get a chance to meet your colleagues in earthquake engineering and to discuss their work face to face. While virtual programs allow the presentation of material, they will never replace the interaction and camaraderie of a real conference. I consider my attendance at past world conferences to have had a profound influence on my research and my understanding of the issues facing earthquake engineers in places I will never have a chance to visit. We work in a field that has no cultural, economic, or geographic boundaries. All of us have the same goal: to reduce the risk that earthquakes pose to our lives and future well-being. And we can only achieve that goal by working together and sharing our knowledge. The theme of my comments will be on the role of observation and creative thinking in earthquake engineering. I was fortunate to have mentors who stressed understanding the behavior of concrete structures through observation of laboratory tests and field performance. They also impressed upon me the need for creative thinking to explain and use those observations for improving structural codes. As an undergraduate at the University of Nebraska, I had an advisor who studied under the legendary Hardy Cross. Cross influenced his approach to teaching and certainly my learning. In graduate school at the University of Illinois, I had many mentors, as Sergio mentioned. Dr. Sees and especially Dr. Sozin influenced my desire to study structures experimentally and to use the observations to improve building codes. My research involved the design and behavior of reinforced concrete floor slabs. At that time, there were several different methods for designing floor systems, and the results could be quite different depending on the method chosen. It was an introduction to the importance of code development and interpretation. That issue has been an important part of my technical committee work ever since. Dr. Cease was a firm believer in participation in technical committees and organizations, and I became a member of the American Concrete Institute as a graduate student. I have always stressed such participation in professional societies and technical committees to my students. Discussions of issues at technical committees gave me valuable insight into the relationship between research, practice, and codes. I would especially urge you to join a technical society related to earthquake engineering in your country or elsewhere. Organizations such as the Earthquake Engineering Research Institute in the US provide a forum for interaction between different disciplines addressing seismic issues. My Illinois mentors also stressed the importance of communicating research findings to the profession. I learned more about clear writing from Dr. Sozin than any other teacher. He reviewed my writing word for word and was always asking, "Is that what you meant?" Clear writing reflects thoughtful study of observations. and we often had long discussions after a test on what we had learned and how to interpret and to present the results. As Sergio so vividly remembers, I tried to follow this approach with my students, and I know they were greatly disappointed when I returned their writing covered in red lines and changed words. But I hope they eventually appreciated getting such feedback as they realized that writing is critical in an engineering career. One admonition from Dr. Cease about writing codes or writing technical papers was that your writing must be clear and understandable, but you must make sure it cannot be misunderstood or misused. This is especially true for writing codes and guidelines. I joined technical committees that included not only researchers, but also practicing engineers. And from the designers, I learned a great deal about the problems they faced and the areas where research could be useful. Their insights into issues where codes and design guidelines were unclear, inadequate, or non-existent were most helpful. Now I would like to briefly discuss some of the areas of research that formed my career. Although I had no formal earthquake engineering courses at Illinois, I observed some of the first cyclic loading tests conducted on reinforced concrete joints. This led me to the study of cyclic and earthquake loadings when I began my research at Rice University. One of my first projects was a study of plain concrete under cyclic axial loadings. Later, we studied the hinging behavior of beams under large cyclic deformations. Then I was fortunate to join a group of researchers at the University of Texas. Professor Ferguson brought together a faculty that had interests similar to mine regarding experimental research. That environment supported my research and teaching for nearly 45 years, and I am grateful to have had such an opportunity. Before I joined the faculty at the University of Texas, Professor Ferguson had studied anchorage and development of reinforcement extensively. Our research extended Professor Ferguson's work through additional tests on splices and anchorages. We proposed new equations for design with variables not included in existing codes. At about the same time, researchers in Germany and Sweden proposed very similar equations, and we were able to corroborate our approaches and coordinate design changes. Modification and improvement of those original equations continues today as new and higher strength materials are used, and additional tests by many researchers clarify some of the assumptions in our equations. Often work published in a journal will stimulate another researcher or student to continue the work and improve our understanding. A few words about the transfer of research to practice. The process may sometimes seem too slow, but changes to codes or the development of new codes requires careful thought and time to evaluate their impact and applicability. Patience and perseverance are essential. When research and courses in earthquake engineering were introduced at the University of Texas, many people asked why. Texas has no history of earthquakes. We had to explain that students from around the world come to study at Texas, and our graduates may work in earthquake regions or for companies that have facilities or projects in those locations. In fact, we all live in earthquake country. At Texas, our first tests of reinforced concrete beam column joints involved very simple setups. To apply cyclic loadings, we had to use hydraulic jacks that could apply loads in only one direction. Reorienting the equipment to complete a loading cycle was a major task, and took days rather than minutes or hours. A picture of the test setup is included in the flyer for the master's program. I mentioned the test procedure only to let you know that it is often best to keep specimens and test equipment simple. Your budget may not permit the purchase of expensive equipment. However, with innovation, imagination, and motivated graduate students, you can accomplish a great deal. The results of those tests were the basis for the first design guidelines for joint detailing in the US. Subsequently, we collaborated with colleagues in New Zealand, Canada, Japan, and China to expand our knowledge of the behavior of joints in reinforced concrete structures. Throughout my career, I have had wonderful opportunities to learn about earthquake engineering through reconnaissance visits to seismic zones in the US and elsewhere. Greece, Japan, Mexico, New Zealand, China, Turkey, and the former USSR, where I visited Russia, Armenia, Georgia, Azerbaijan, and Kazakhstan. Observations of damaged buildings and local construction practices in those places shaped my research into the detailing of reinforced concrete structures. Several issues stood out from the observations. The lack of attention to details of reinforcement, especially in columns and joints. Those inadequate details led to failure of members and often collapse of the structure. From examination of codes that were used in the design of the damaged structures, it was apparent that such details were never covered. Therefore, engineers did not include them in the design. Such deficiencies included bars that were not anchored in confined concrete, splice lengths that were too short or in the wrong direction, or in the wrong location, ties and stirrups that were too far apart to provide confinement or were not included in the joint. And sometimes the members and joints were just too small to carry the forces or deformations imposed during the earthquake. As we learn more about the behavior of reinforced concrete members under various cyclic loadings, the influence of bidirectional effects became an issue. To study such loadings, we received funding from the U.S. National Science Foundation to build a test floor and wall system in our Texas laboratory so that forces in two lateral directions and axially could be applied to a test specimen. Using the new facility, we tested columns and beam column joints under bidirectional forces. Two graduate students from Japan, who many of you know, Dr. Kyuichi Maruyama and Dr. Hidetaka Umehara, participated in that program. It also became evident that in addition to improving codes for new building construction, guidelines for retrofitting and strengthening existing structures were needed. Almost no guidelines were available that addressed those issues. To help us design tests that would provide information for designers and were representative of existing inadequate structures, we engaged partners from the design world. Degenkolb engineers from San Francisco became part of our research team. They were deeply involved in the design of seismic rehabilitations for a variety of buildings with deficiencies. Degenkolb engineers visited our lab to plan test programs, view tests, and discuss results. That partnership facilitated the transfer of our test results to practice almost immediately. I will always be grateful to my friend and colleague, Loring Wiley, for his role in our work. After the 1985 Mexico City earthquake, we organized several workshops involving researchers and practicing engineers from Mexico and the US to provide guidance on research needs related to existing buildings. The research that was developed brought Dr. Alcocer to Texas and was the start of our long friendship and collaboration. Those workshops were especially important because the earthquake was a real-time test of some buildings that were rehabilitated before the earthquake. Perhaps the most important aspect of that workshop was that many of the structural engineers involved in rehabilitation projects from Mexico and the US had a chance to share their approaches and to discuss their concerns. The 3D test facility and the research on bidirectional loadings led to my participation in perhaps the most exciting and rewarding project of my career. The US-Japan program on large-scale testing was organized to take advantage of a new test facility that was built in Tsukuba, Japan at the Building Research Institute. Two prominent earthquake engineers, Professor Joe Penzine of UC Berkeley and Professor Hajime Umemura from the University of Tokyo, led the program. Practicing engineers and researchers from both countries worked together to develop a series of tests on various earthquake-resisting structural systems. The first test was a full-scale, 7-story reinforced concrete structure designed to reflect building practices in both countries. At Texas, we tested a number of large-scale beam column joints so that their behavior could be compared with similar regions of a complete structure. During this time, a number of visiting researchers from Japanese construction companies and universities came to Texas, and their contributions to our research and to earthquake engineering were exceptional. Over the years, I had many opportunities to visit Japan and meet friends and colleagues, especially Professor Hiro Aoyama, a lifelong friend. Those visits always reminded me of the importance of interaction between engineers from different countries and sharing knowledge to reduce earthquake risk for all. I would like to mention two colleagues, Professor Roberto Melli from Mexico and Dr. Shunsuke Sugano from Japan, whose advice and encouragement were invaluable to our research on rehabilitation. Finally, I would like to say a few words about the last major research project I was involved with for retirement. As part of our work on earthquake rehabilitation of structures, we examined the use of carbon fiber reinforced polymer materials. Using those results, we were successful in securing support from the Texas Department of Transportation for large-scale tests of bridge girders strengthened using CFR materials and to develop a design procedure for such girders. This is an example of working with design and construction engineers to adapt research from one area to solve problems in another area. For young researchers, and also those who may not be so young, who are looking for problems to solve, I urge you to make contact with designers and builders and learn about their problems and frustrations. Their advice and experience will be invaluable to you as you develop research ideas and advance your careers. So let me offer some closing comments. I have had the privilege of working with many talented and extremely dedicated graduate students who have been the main contributors to the success of our projects. I have received great support from my faculty colleagues. I have cherished the camaraderie of colleagues from other universities. I appreciate all the opportunities I have had to interact with practicing engineers who shared their knowledge with me. I would like to have mentioned each of these individuals, but that time is too short. You should be mindful that an engineering career is a collaborative effort. We do not succeed alone. Our success comes from the guidance of our teachers and mentors, the efforts of all the students who work with us, the support of our colleagues, and above all, the encouragement of our families and friends. Always remember and cherish and acknowledge that help. Thank you again for the honor of visiting with you.